Before we begin today's journey into the great dying Earth's most devastating extinction, thank you for spending your time here. If you enjoy quiet science-based stories like this, please consider leaving a like, subscribing to the channel, and sharing this video with someone who would enjoy listening too. It really helps this project continue. I would also love to know what time of day are you listening and where in the world are you watching from. Feel free to share it in the comments below. Now let's slow down, get comfortable, and begin. The story of the Great Dying sits within a stretch of late Permian time that lies more than 250 million years in the past, at a point when Earth already carries a long history of changing oceans, drifting continents, and evolving life. In this interval near the end of the Permian and close to the boundary with the earliest Triassic, the planet presents a recognizable but unfamiliar arrangement. Most of the land is gathered into a broad mass, the seas wrap almost entirely around it, and the poles lie at the far edges of a world that is generally warmer than the present. The surface of the planet is quiet in the sense that its large-scale patterns appear stable when viewed over human spans of time, but in geological terms this is only a temporary arrangement within a much longer chain of slow change. Geologists later give names to these slices of time and to the rocks that form in them, yet in the late Permian itself there is only a continuous planet with continents, oceans, atmosphere and biosphere interacting every day. At this stage, the outer frame of the world is defined by the presence of the supercontinent configuration, by a single great surrounding ocean basin, and by belts of shallow seas that fringe the coasts of the main landmass. Mountain belts rise where plates have long since collided. Broad lowlands stretch between them, crossed by rivers that wander out toward the sea. Continental shelves form wide submerged platforms around the margins of the land, and beyond these shelves the sea floor falls away into deeper basins that are dim cold and distant from shore. The planet rotates under a sun that delivers uneven warmth to low and high latitudes. Around the equator sunlight arrives more directly, and for longer each day, and the waters and lands there are generally warm. Toward the poles sunlight comes in at a lower angle, and for shorter periods, and the air and seas are generally cooler, although still milder overall than in many later cold periods of Earth history. Seasonal changes in the tilt of Earth's axis bring alternating phases of warmer and cooler months, shifting rainfall and winds across the joined continents. Over the course of many thousands of years, the pattern of climate zones slowly migrates as plates continue to move and as the long-term balance between incoming solar energy and outgoing heat from Earth's surface adjusts by small amounts. Seen at the broader scale, the late Permian planet is one where dry continental interiors, more humid coastal regions and expansive ocean basins coexist in patterns set by latitude, elevation, and distance from the sea. On land, this outer frame of geography and climate allows a variety of environments. In some regions, extensive river systems cross wide floodplains, leaving layers of sand, silt, and mud that will later become rock. Elsewhere, low coastal plains pass gradually into swampy ground and deltic settings where plants grow densely in waterlogged soils. In other places, highlands channel rainfall into narrower valleys, while more central continental areas receive little precipitation and support dry steppe or desert conditions with sparse vegetation. Across these landscapes, plants, invertebrates and vertebrates inhabit niches shaped by temperature, moisture, and the availability of shelter and food. But at this level of description, what stands out is the overall continuity of the land surface and the strong contrast between moist margins and drier interior zones. The oceans fit around this landmass and provide another broad setting. Shallow shelf seas along the margins of the supercontinent host diverse marine communities, especially where clear warm waters and stable substrates permit the growth of reefs and other complex structures on the seafloor. Slightly farther from shore, continental slopes lead down into deeper water, where light levels fall and conditions favour different assemblages of organisms adapted to cooler, darker and higher pressure environments. The deepest basins lie still farther out, where the sea floor receives a slow rain of organic material and mineral particles from the surface waters above. Currents driven by wind temperature differences and the rotation of the planet link surface and deeper layers and help distribute heat gases and nutrients throughout the global ocean. They also influence where oxygen-rich waters reach the seafloor and where more stagnant conditions persist, shaping broad patterns in marine habitability from one region to another. The atmosphere completes this outer picture. It consists of a mixture of gases that has been shaped over long spans of Earth history by volcanic outgassing, chemical weathering at the surface, and most importantly by the collective activity of photosynthesizing and respiring organisms. In the late Permian, the air holds enough oxygen to support active animal life on land and in the sea, and it holds greenhouse gases such as carbon dioxide at levels higher than many present-day values, helping maintain generally warm global conditions. Winds blow from regions of high pressure to regions of low pressure, guided by the rotation of the planet and the distribution of land and sea, so that large-scale circulation cells move heat and moisture from equatorial to higher latitudes. Clouds form where moist air rises and cools, delivering rain or snow that feeds rivers, sustains vegetation, and shapes the surface through erosion. Across tens of millions of years, the combined action of these processes builds up the sedimentary layers that later reveal, this time to researchers, river deposits on continents coastal and shallow marine strata around the margins, and deep sea sediments spread thinly over the basin floors. In the moment, however, the late Permian Earth is simply a functioning system with continents, ocean, and atmosphere linked through the flow of energy and matter. Continental outlines, ocean basins and climate zones control where energy, water, and materials move through the system, and how environments are distributed across the planet, forming the broad outer context of the late Permian world as it exists during this interval of Earth history. The supercontinent that dominates late Permian Earth links almost all major land areas into one continuous mass that stretches from high southern latitudes to high northern latitudes. This configuration is often called Pangaea, and it acts as a single vast block that interrupts the flow of air and ocean around the globe. Around it lies a single main ocean basin, the Panthalassic Ocean, while to one side, along embayment, the Tethyan realm forms a complex zone of narrower seas and continental margins. As this connected landmass rotates each day beneath the sun broad climate, belts arise from the interplay of latitude topography and distance from the sea. These belts are not rigid lines but wide zones, where certain conditions are more likely than others, and they shift over geological time as plates continue to move. Even so, at the scale of several million years near the end of the Permian, the pattern is stable enough to leave a consistent imprint in rocks, fossils, and sedimentary structures that later record this world. Around the equator, the sun stands higher in the sky, and the surface receives more direct solar energy through the year. Warm air over these low-latitude regions tends to rise, lose moisture as rain, and then move poleward at higher altitudes before sinking again at subtropical latitudes. Over the Panthalassic Ocean, this circulation pattern promotes broad bands of rising moisture-laden air near the equator and descending drier air to the north and south. Where this circulation interacts with the margins of Pangaea, it shapes prevailing winds and rainfall along the coasts. Low-latitude coastal regions on the windward sides of the supercontinent receive frequent rain, maintaining rivers, wetlands, and dense vegetation in some areas. On the leeward sides and farther into the interior, the air has already lost much of its moisture, so the continents support drier climates with more seasonal or limited rainfall. Because so much land is gathered together, the distance from some interior sites to the nearest ocean is very large. These continental interiors respond more strongly to seasonal heating and cooling than coastal regions, which are buffered by nearby seas. In summer, interior lowlands and plateaus warm, deeply raising air temperatures and promoting intense convection, and storms where moisture is available. In winter, the same interiors cool more sharply, allowing cold, dense air masses to form. The contrast between interior and coastal regions influences pressure patterns and the direction and strength of winds that blow across Pangaea. In some belts, the pattern resembles large monsoon-like systems, where winds reverse seasonally as the thermal contrast between land and sea grows and then relaxes through the year. In wet phases, air from the ocean flows onshore, climbs over warm land, and drops rain across coastal and near-interior regions. In dry phases, air flows offshore, reinforcing arid conditions in continental interiors and leaving evidence of evaporation and limited vegetation in the sediments that accumulate there. Topography adds another layer to this climate map. Mountain belts raised by previous collisions of smaller land masses that built Pangaea form long chains that run across parts of the supercontinent. These ranges intercept moist air moving inland from the ocean. On their windward flanks, air is forced to rise, cool, and drop its moisture as rain or snow feeding rivers and supporting forests and other plant communities. On their leeward flanks, descending air is drier and warmer, creating broad rain shadow zones that extend far into the interior. The combination of latitude elevation and position relative to these ranges produces a patchwork of local climates nested within the broader belts. High plateaus at moderate latitudes may be cool and seasonally wet, while low basins at similar latitudes may be warm and arid. Coastal plains near the Tethyan margins may enjoy humid conditions and long-growing seasons, while inland regions at the same latitude experience far greater extremes between wet and dry periods. At higher latitudes, both north and south, the angle of incoming sunlight is lower, and the seasonal contrast in day length is greater. These regions are cooler on average than low latitudes, although in the late Permian they are still milder than polar regions in many later icehouse periods. Snow and ice may accumulate in some high elevation or high latitude areas during cold seasons, but evidence for large persistent ice sheets is limited in many reconstructions. Instead, these parts of Pangaea likely support cool temperate climates, with seasonal freezing variable precipitation and vegetation adapted to shorter growing seasons. Storm tracks guided by the temperature difference between warm subtropical and cooler polar air masses sweep across these belts, bringing variable weather to the mid-latitudes of the supercontinent. The surrounding oceans help mediate the extremes of this supercontinental climate. Currents in the Panthalassic Basin move warm surface waters away from low latitudes and return cooler waters from higher latitudes, while deep currents circulate more slowly at depth. Where these currents approach the margins of Pangaea, they influence coastal temperatures and humidity. Western margins facing the prevailing winds may receive relatively mild wet conditions, while eastern margins may be influenced more by continental air. The Tethyan realm, with its narrower seaways, island arcs, and submerged platforms, provides a different pattern, with more enclosed water bodies that can warm and evaporate strongly under the subtropical sun. These settings generate local humidity clouds and rainfall patterns that produce lush coastal belts and shallow marine environments with distinctive ecological and sedimentary signatures. Across the whole of Pangaea and its surrounding seas, the result is a connected but varied climate system. Broad belts of tropical, subtropical, temperate and higher latitude conditions wrap around the globe, but within each belt, the details depend on distance from the sea elevation and position relative to prevailing winds and currents. In some places, river systems drain vast catchments and deliver large volumes of sediment to coastal plains and deltas. In others, evaporation exceeds precipitation, and salts accumulate in closed basins, while dunes migrate across dry lowlands. Vegetation patterns track these gradients with dense plant cover in warm, moist regions, more open woodlands and shrublands in seasonal climates, and sparse or patchy cover in the driest interior zones. Together, these elements define the spatial framework of late Permian climate over the supercontinent, and its oceans setting a pattern of heat, moisture and circulation that governs how energy and materials move through the outer parts of the Earth system during this interval. The late Permian oceans and atmosphere together form a linked part of the Earth system that appears steady when viewed on human timescales, even though it is shaped by slow, ongoing processes acting over millions of years. The global ocean covers most of the planet and is divided into surface intermediate and deep layers that differ in temperature, salinity and chemical properties. Warmed by sunlight, the uppermost layer is relatively light and buoyant, and it is stirred by winds that blow across the sea surface. Waves and turbulence mix the upper tens to hundreds of meters, creating a layer in which temperature and dissolved gases are fairly uniform, especially away from strong fronts or upwelling zones. Below this mixed layer, temperature generally decreases and density increases with depth, forming a more stratified water column, in which vertical movement is slower and more constrained. At the broadest scale, the circulation of this ocean is driven by the combined action of wind at the surface and differences in density within the water. In low-latitude regions, strong sunlight keeps the surface waters warm and inhibits mixing with deeper, cooler layers. In higher latitude regions, cooler air and lower solar input help the surface cool, and in some places higher salinity, resulting from evaporation or from the formation of seasonal sea ice, increases the density of surface water. Where surface water becomes dense enough, it can sink and move along the seafloor as a deep current. Over long distances, these density-driven flows connect distant basins and help carry oxygen, rich water from the surface into the ocean interior. Wind-driven currents also play a major role. Persistent winds push surface waters so that they form large gyres in the main Panthalassic Basin and more complex patterns in the narrower Tethyan realm. Where winds drive surface waters away from a coast or cause divergence in the open ocean, deeper water must rise to replace it. This upwelling brings cooler nutrient-rich water toward the surface. Where winds cause convergence, surface water is forced downward in downwelling zones that help carry oxygen into the interior. The balance between these processes controls how heat, oxygen, and nutrients are distributed vertically and horizontally within the ocean. In the late Permian, many reconstructions suggest that large portions of the deep ocean remain relatively well oxygenated, supported by sufficient ventilation from high-latitude sinking and from areas of downwelling. Oxygen enters the ocean at the surface where the atmosphere and sea are in contact, and where photosynthetic organisms add oxygen during the day. As water masses move into the interior, they carry this dissolved oxygen with them. Organisms living in deeper waters consume oxygen as they respire, and as organic matter sinks and decays, so the concentration decreases along the flow path. If ventilation is strong and the rate of oxygen consumption is moderate, deep waters can remain hospitable to a wide range of animals and microbes that require at least some oxygen to survive. In regions where circulation is sluggish, or where high productivity at the surface produces large amounts of sinking, organic matter, oxygen can become depleted at intermediate depths, forming oxygen minimum zones. These zones restrict which organisms can live there and influence where nutrients are regenerated and returned to the surface. Overall, however, the pre-crisis ocean supports extensive and diverse marine ecosystems across many depth ranges and climate zones. Surface waters in warm, clear, shallow seas along the continental margins host reefs and other complex communities. Planktonic organisms inhabit the sunlit upper ocean, forming the base of many food webs. Nectonic animals, including various fishes and cephalopods, swim through the water column, while benthic organisms live on or within the seafloor sediments. The patterns of diversity and abundance vary from region to region, but the underlying physical and chemical environment remains within ranges that marine life has adapted to over long spans of time. The atmosphere above these oceans provides the medium in which gases, water vapor, and energy move around the planet. Its composition has been influenced by billions of years of interaction between volcanic outgassing, rock weathering, and biological activity. In the late Permian, the air contains nitrogen as its dominant component with oxygen, making up a substantial fraction that is adequate to support active aerobic life on land and in shallow waters. Carbon dioxide is present at levels higher than many present-day values, contributing to a strong greenhouse effect that keeps global temperatures relatively warm. Water vapor content varies from place to place, and over time, depending on temperature and proximity to moisture sources such as the oceans. The vertical structure of the atmosphere features a lower layer, the troposphere, in which temperature generally decreases with height, and where most weather processes occur, and higher layers that interact with incoming solar and cosmic radiation. Ozone in the upper atmosphere absorbs a share of the sun's ultraviolet radiation, providing a protective screen that limits the most damaging wavelengths from reaching the surface in high intensities. Within the troposphere, patterns of rising and sinking air create circulation cells that guide the major wind belts. Near the equator, warm air rises in a broad zone of low pressure, releasing latent heat as water vapor condenses into clouds and rain. Aloft, the air flows poleward and eventually sinks in subtropical high-pressure belts, where skies are often clearer and surface conditions drier. Farther poleward, additional circulation cells operate shaped by the temperature contrast between the tropics and the poles and by the rotation of the planet. These cells, combined with the positions of continents and oceans, determine the prevailing winds that move moisture and heat from one region to another. The coupled ocean atmosphere system is sustained by a steady input of solar energy and by the long-term cycling of carbon and other elements between reservoirs. Chemical weathering of rocks on land consumes carbon dioxide from the atmosphere, transporting dissolved ions to the sea, where they may be buried in sediments as carbonates. Volcanic and metamorphic processes return carbon dioxide and other gases to the air over millions of years. Photosynthesis in the surface ocean and on land draws down carbon dioxide and releases oxygen, while respiration and decay return carbon dioxide to the air and water. Over the late Permian interval before the main crisis, this cycle appears to operate within bounds that keep climate-ocean chemistry and atmospheric composition in a state that, while not static, does not depart abruptly from established ranges. Fluctuations occur on shorter timescales, and regional conditions can change significantly from place to place, but the overall structure of circulation, oxygenation, and gas balance remains coherent enough to support the diverse biosphere that has developed by this point in Earth history. Over long spans of late Paleozoic and early Permian time, the apparent stability of the late Permian world rests on deep processes that have been active for tens of millions of years beneath the surface. Tectonic plates driven by mantle convection and by the sinking of old dense lithosphere at subduction zones continue to move, collide and separate. These motions gradually assemble the supercontinent from smaller blocks and island arcs, closing older ocean basins and reorganizing the boundaries between land and sea. As continents converge, rock at their leading edges is crumpled, thickened and uplifted to form mountain belts. As plates slide past or pull apart, rifts open, and volcanism takes place along new or reactivated fractures. None of these processes is sudden on human timescales, but over geological intervals they alter the geography, relief and stress patterns of the crust, setting the stage on which later events unfold. In the late Permian, the assembly of Pangaea is mostly complete, yet the crust still records the strain of past collisions and the adjustments that follow them. Deep roots of mountain ranges continue to rise and erode. Sediments shed from these uplands accumulate in adjacent basins, loading the lithosphere and influencing how it flexes. Magmatic systems that accompanied earlier convergent and collisional phases linger beneath some regions, cooling and crystallizing slowly, or feeding smaller episodes of intrusion and eruption. Together, these processes provide a background level of tectonic and volcanic activity that influences the slow evolution of landscapes, climates, and habitats. Over similar timescales, the carbon cycle responds to the changing distribution of continents, mountain belts, and oceans. Elevated regions with fresh, easily weathered rock surfaces enhance chemical weathering, which consumes carbon dioxide from the atmosphere and delivers dissolved ions to rivers and seas. In contrast, low-relief regions with older, more stable surfaces may contribute less to this drawdown. When land plants expand into new areas, their roots and associated microbes further promote weathering, linking biological evolution to carbon cycle feedbacks. Burial of organic matter in sediments sequesters carbon over long periods, while metamorphism and volcanism return it to the atmosphere. The balance between these processes controls the long-term level of greenhouse gases in the air and therefore the baseline climate state. During the late Paleozoic, there is evidence for intervals of extensive glaciation, particularly in the southern parts of the supercontinent, followed by a general trend toward warmer, less ice-dominated conditions by the late Permian. This shift suggests that over millions of years the carbon cycle has moved from a state that favours widespread ice sheets and cooler climates to one that supports warmer polar and mid-latitude conditions, even though regional and shorter-term variations continue. In the oceans, long-term changes in basin configuration and seafloor spreading also influence circulation patterns and the distribution of mid-ocean ridges and volcanic arcs, which in turn affect the release of heat and gases into the water and atmosphere. Seafloor spreading centres and volcanic arcs emit carbon dioxide, water vapour, and other gases adding to the atmospheric reservoir. If spreading rates increase over an extended interval, the additional outgassing can contribute to higher greenhouse gas levels, all else being equal. Similarly, the area and depth distribution of ocean basins influence how much water can be stored at different temperatures and salinities and how easily deep waters can form and rise. The late Permian Ocean, with its large panthalassic basin and complex Tethyan margins, reflects the cumulative result of these plate tectonic processes. At the same time, the biosphere has been changing. By the late Permian, both marine and terrestrial ecosystems are the products of repeated radiations and extinctions. Earlier crises, including significant biodiversity losses in the late Devonian and other intervals, have already reshaped life in previous periods. Reef-building communities have shifted in composition more than once as different groups of organisms take on the role of constructing complex three-dimensional habitats in shallow seas. On land, forests composed of different plant lineages have expanded and contracted with climate changes and with the rise of new forms of herbivores and decomposers. Vertebrate faunas, both in the water and on land, show patterns of diversification and replacement as lineages adapt to new roles and as older groups decline. Against this background, the late Permian world appears rich and varied, yet also carries signs of ongoing ecological adjustment. In some records, there are hints of stress or change leading up to the final Permian boundary, such as shifts in species composition evidence for fluctuations in sedimentation patterns or variations in geochemical indicators that track productivity, redox conditions, or the input of weathering products from land. These signals are not uniform everywhere, and their interpretation is still the subject of active study, but they suggest that the Earth system is not entirely static even before the main extinction interval. Episodes of local or regional environmental disturbance, including smaller-scale volcanic events, climate swings or sea level changes, continue to affect particular basins and continents. Some groups may experience gradual declines or stepwise losses, while others maintain or even expand their ranges, depending on how their ecological requirements match the evolving conditions. Over the span of several million years before the end Permian boundary patterns of tectonic activity, magmatism, erosion, and carbon cycling build a context in which the atmosphere and oceans become sensitive to additional forcings. The climate is relatively warm, ice sheets are reduced compared with earlier times, and many ecosystems operate near the limits set by available oxygen, temperature tolerance, and nutrient supply. In such a state, added inputs of greenhouse gases or other perturbations have the potential to produce outsized effects compared with similar inputs under different baseline conditions. The accumulation of these slow changes does not yet constitute a singular global crisis, but it prepares the physical and chemical framework of the planet, in which a large sustained pulse of volcanism or another major forcing, when it occurs, can interact with existing trends in ways that more strongly disturb the balance of the late Permian Earth system. Deep beneath the northern part of the late Permian supercontinent, a large volume of mantle begins to rise toward the base of the lithosphere. This rising body, often described as a mantle plume, represents hotter-than-average rock that moves slowly upward because it is slightly less dense than the surrounding mantle. As it approaches shallower levels, pressure decreases and parts of the plume begin to melt, producing large amounts of basaltic magma, unlike the narrow volcanic arcs that form above subduction zones. This setting creates a broad zone of melting within continental crust that is already under stress from past collisions and ongoing adjustments. Over time, the plume head spreads out against the base of the lithosphere, weakening it and promoting intrusion of magma to the lower crust. Eventually, fractures and zones of weakness allow some of this magma to ascend toward the surface. In what will later be called the Siberian region, repeated episodes of magma ascent and eruption build up one of the largest known continental flood basalt provinces in Earth history. At the surface, the style of volcanism is different from steep cone-building eruptions. Instead, fissures and vent systems open along fractures, and low-viscosity basaltic lava pours out over wide areas. Individual flows can travel many kilometers from their sources, filling lowlands and covering older landscapes in broad, relatively thin sheets. Over many thousands of years and through numerous eruptive pulses, these sheets stack on top of one another to form thick sequences of basalt. Later erosion and uplift will reveal them as step-like landscapes of dark volcanic rock, giving rise to the term traps. But at the time of emplacement, they are simply extensive lava fields spreading over the continent. The total area eventually covered approaches several million square kilometers, and the total volume of erupted basalt reaches many millions of cubic kilometers when all individual flows and intrusive bodies are taken into account. The activity is not a single brief outburst, but a prolonged episode with variations in intensity. Some intervals are dominated by relatively low level effusion, where lava continues to emerge from vents and fissures at rates that fill depressions and build thick plateaus without producing extreme explosive activity. Other intervals may involve more energetic events, especially where magma interacts with groundwater or surface water, or where more gas-rich batches reach the surface. In these cases, fragmentation of magma can generate ash and pyroclastic material that is dispersed regionally. In addition to surface flows, large volumes of magma stall within the crust as sills and dikes. Sills spread laterally between existing rock layers while dikes cut upward through them. These intrusions can heat and alter the surrounding rocks, causing them to release fluids and gases or to undergo partial melting. In the late Permian-Siberian region, the crust includes thick sequences of sedimentary rocks, some of which contain organic rich layers, carbonates, evaporites, and other compositions that respond strongly to heating. When hot basaltic sills are emplaced into such strata, contact metamorphism occurs, driving off volatile components and producing additional fluids and gases that can migrate toward the surface through fracture networks. The main eruptive phase of this large igneous province spans on the order of 1 million years, although there is uncertainty in the precise duration and in the exact timing of individual pulses. Radiometric dating of minerals within the basalts and associated rocks combined with correlation to sedimentary sequences elsewhere shows that much of the activity is clustered around the time of the Permian-Triassic boundary. Some data suggest that the highest eruption rates may occur over shorter intervals within this broader span, while lower-level magmatism persists before and after these peaks. This pattern is consistent with an initial arrival of the plume head, followed by a series of major outpourings and then a gradual waning phase as the system cools and evolves. Throughout this episode, the region experiences repeated resurfacing by lava flows, burial of earlier landforms, and the development of thick piles of volcanic and subvolcanic rock. Local ecosystems near the vents and flow fields are directly affected by burial heat and ashfall. Rivers are dammed or rerouted by lava lakes are filled, and soils are covered. The regional topography changes as basins fill with basalt and new highlands form from stacked flows. Over longer distances, volcanic plumes inject particles and gases into the atmosphere, though the height, composition and persistence of these plumes depend on eruption-style vent geometry and climate conditions at the time. In addition to the visible eruptions, the ongoing intrusion of magma into the crust continues to alter deep and shallow rock volumes. Where intrusions intersect coal-bearing strata or other carbon-rich sediments, heating can generate methane, carbon dioxide and other gases that may escape through fractures and vents. Where intrusions encounter evaporites, rich in chlorine, fluorine or sulfur-bearing minerals, they can release halogen and sulfur-containing gases. The balance between gases released directly from magma and those produced by heating of surrounding rocks is still an area of active study and estimates vary, but it is clear that the total volatile output of such a province over its lifetime is very large. Against the global background of late Permian tectonics, the Siberian flood basalts therefore represent an exceptional concentration of magmatic and intrusive activity in both space and time. They inject heat and magma into the lithosphere over a broad area, create thick volcanic plateaus at the surface, and provide numerous pathways for gases and fluids to move from deep reservoirs into the atmosphere and hydrosphere. Because this province develops within continental crust far from an active plate boundary, it stands out among other volcanic settings of the time and marks a distinctive long-lived episode of mantle-derived activity within the wider late Permian Earth system. Over the course of its development, this activity transforms a large region of the northern supercontinent into a volcanic and intrusive complex that remains a persistent high-level source of thermal and chemical input to the surrounding environment. As the Siberian flood basalt province develops, it becomes a major long-term source of gases and particles to the atmosphere. Each eruption, whether a brief pulse or a more extended effusive episode, releases volatiles that were dissolved in the magma or produced by heating of surrounding rocks. Over the full duration of activity from its early pulses through its peak and into its waning stages, the cumulative release of gases builds into a forcing on the climate system that is large compared with many background sources. The most important components for global energy balance are carbon dioxide, methane, and water vapour, although other gases, including sulfur-bearing species and halogen-bearing compounds, also play significant roles in controlling radiation and atmospheric chemistry. Basaltic magmas typically carry substantial amounts of carbon dioxide and water. When these magmas approach the surface and pressure drops dissolved, gases exsolve to form bubbles and are emitted into the atmosphere during eruptions. In the case of the Siberian province, the sheer volume of magma involved means that even moderate gas contents yield large total outputs when integrated over many eruptions. In addition, contact metamorphism of carbon-rich sediments intersected by intruding sills and dikes produces further carbon dioxide and methane. As hot magma heats coal measures organic-rich shales and other carbon-bearing rocks, these strata break down thermally and release gas mixtures that can migrate upward through fracture systems. Together, primary magmatic degassing and secondary heating of sediments form a combined carbon source that adds to the atmosphere over hundreds of thousands of years. Methane generated in this way is a particularly strong greenhouse gas on short timescales. In the atmosphere, it oxidizes to carbon dioxide over years to decades, but before that conversion, it enhances the trapping of outgoing long-wave radiation, contributing to warming. Carbon dioxide persists much longer, being removed from the atmosphere only gradually through ocean uptake and chemical weathering on land. As repeated eruptive and intrusive episodes add pulses of these gases, the atmospheric burden of greenhouse gases increases. The exact rate of increase and the total peak concentrations are uncertain and depend on assumptions about gas contents, eruption timing, and feedbacks in the carbon cycle. But many reconstructions indicate a substantial rise relative to pre-event levels. At the same time, other components of volcanic emissions influence climate in more complex ways. Sulfur-bearing gases such as sulfur dioxide are released directly from magma and can also be generated by heating of sulfur-rich sediments. In the lower atmosphere, these gases can oxidize to form sulfate aerosols, tiny droplets or particles that reflect and scatter incoming solar radiation. If such aerosols reach the stratosphere and persist there, they can produce a temporary cooling of the surface by reducing the amount of sunlight that reaches the ground and ocean surface. For short-lived eruptions, this cooling is often limited to a few years, but in the case of a long-lived large igneous province, repeated injections of sulfur could maintain elevated aerosol loading for extended intervals, especially during periods of intense activity. This introduces a potential pattern in which rapid, short-term cooling episodes associated with aerosol pulses are superimposed on a longer-term trend toward warming driven by accumulating greenhouse gases. In the immediate aftermath of large eruptions, regional or even global temperatures near the surface may drop, weather patterns may shift, and the hydrological cycle may respond to decreased solar input. As aerosols settle out or are removed by chemical reactions, their cooling influence wanes, but the longer-lived greenhouse gases remain. The net climatic effect over tens to hundreds of thousands of years is then dominated by warming, even if individual decades or centuries experience cooler conditions tied to specific eruptive episodes. Halogen-bearing gases form another important component of the emissions. Heating and metamorphism of evaporites, which can be rich in chlorine and fluorine as well as magmatic degassing, can release hydrogen chloride, hydrogen fluoride, and related compounds. Some of these halogens can reach the stratosphere where they participate in catalytic cycles that destroy ozone. Ozone in the upper atmosphere plays a crucial role in absorbing ultraviolet radiation from the sun. When ozone concentrations decrease, more ultraviolet radiation of certain wavelengths can reach the lower atmosphere and surface. The degree of ozone depletion and its spatial pattern depend on the amount, timing, and altitude of halogen injection, as well as on background atmospheric conditions. Studies of other volcanic events and of modern atmospheric chemistry suggest that sustained or repeated inputs of halogens at sufficient altitude could significantly damage the ozone layer over regional to global scales. If similar processes operate during the Siberian basaltic episode, the result would be a thinning of the protective ozone screen. This would alter the spectral composition of sunlight reaching the top of the troposphere and the surface, potentially increasing the flux of biologically damaging ultraviolet radiation in some regions and seasons. At the same time, changes in ozone also affect the temperature structure of the stratosphere, which feeds back on circulation patterns and the distribution of other trace gases. The combination of greenhouse gas build-up aerosol production and ozone layer modification leads to a complex pattern of radiative forcing. Greenhouse gases increase the downward flux of long-wave radiation, tending to warm the surface and lower atmosphere. Sulfate aerosols reflect and scatter incoming shortwave radiation, tending to cool the surface, and in some cases warm the lower stratosphere where they reside. Ozone changes can either warm or cool different layers of the atmosphere, depending on the direction of change and on altitude. Because these forcings operate simultaneously, but on different timescales and in different parts of the atmosphere, the climate response is not uniform in space or time. Some intervals may be characterized by strong surface warming and intensified hydrological cycling, while others may see transient cooling or altered storm tracks associated with aerosol or ozone variations, all within the broader context of a rising greenhouse gas background. Over the course of the main eruptive phase, the long-lived greenhouse component accumulates in the atmosphere more persistently than aerosols or many reactive gases. The carbon cycle responds by increasing uptake in the oceans and on land, but its capacity to counteract sustained input is limited on the timescale of rapid volcanic degassing. As a result, mean global temperatures trend upward relative to pre-volcanic conditions even as short-term fluctuations occur. This evolving balance in the atmosphere sets new boundary conditions for the oceans and continents below, changing the baseline energy budget and the character of the air and radiation field that interact with the surface of late Permian Earth. As greenhouse gases accumulate in the atmosphere over the main interval of Siberian flood basalt activity, the climate system begins to shift away from the late Permian baseline toward a warmer state. The long-term radiative forcing from higher carbon dioxide and methane levels raises the average temperature of the lower atmosphere and surface, even though short-lived aerosol pulses may briefly mask or complicate this trend in some periods. Land areas warm more strongly than the oceans because they have a lower heat capacity and respond more quickly to changes in radiation balance. Within the supercontinent interior regions, far from the moderating influence of the ocean, experience particularly large seasonal and long-term temperature changes. Summers become hotter, and in some models and reconstructions longer, in their duration of high daytime temperatures. Winters in many mid-latitude interior areas remain cooler than summers, but may also become milder on average compared with earlier intervals, reducing cold season snow cover and altering the timing of freeze and thaw cycles. This warming extends toward higher latitudes as well, shrinking the range of conditions that favour any remaining seasonal snow and ice, and changing the gradients that drive atmospheric circulation. Over the oceans, the mixed layer absorbs heat from the overlying air and from increased downward long-wave radiation, leading to higher sea surface temperatures. Because water has a high heat capacity, and because heat can mix downward over time, sea surface warming may lag behind land warming in some regions, but as greenhouse gases continue to rise, the ocean surface steadily gains heat. The pattern of warming is not necessarily uniform. Low-latitude regions that are already warm may see smaller absolute changes than high-latitude regions, where initial temperatures are lower and feedbacks associated with changing snow and ice cover can amplify warming. However, even modest increases in sea surface temperature can have important consequences, because the solubility of oxygen and other gases in seawater decreases as temperature rises. Warmer surface waters therefore carry less dissolved oxygen at equilibrium, with the atmosphere reducing the maximum amount of oxygen that can be supplied to deeper layers through downwelling and circulation. At the same time, a warmer atmosphere accelerates the hydrological cycle. Higher temperatures increase evaporation from the ocean surface and from wet land regions. The atmosphere can hold more water vapor, which acts as an additional greenhouse gas, and also fuels more intense precipitation events, where air masses converge and rise. In coastal and some monsoon-influenced regions of Pangaea, wet seasons may become more extreme with heavier rainfall and stronger river discharge, while dry seasons become hotter and more prone to drought. In the continental interiors, if circulation patterns lead to reduced moisture delivery, evaporation can outpace precipitation by an even larger margin, enhancing aridity and promoting expansion of desert or semi-desert conditions. Soil moisture declines in many regions, vegetation cover thins or shifts toward drought-tolerant forms, and the contrast between wetter margins and drier interiors of the supercontinent sharpens. These changes in temperature and moisture patterns affect the winds that drive surface ocean currents and influence where deep water forms. In a warmer world with reduced meridional temperature gradients in some layers and changes in sea ice distribution, the loci of deep water formation can move or weaken. If high-latitude surface waters become fresher due to increased precipitation and runoff, or remain too warm and buoyant, their tendency to sink and ventilate the deep ocean diminishes. This reduces the rate at which oxygen-rich surface waters are supplied to the ocean interior, especially to intermediate and deep layers in some basins. At the same time, higher temperatures and enhanced nutrient delivery from intensified weathering and river input can increase biological productivity in certain coastal and shelf seas. More organic matter is produced in surface waters and sinks into deeper layers where it is decomposed by microbes that consume oxygen. The combination of reduced oxygen supply from weakened overturning and increased oxygen demand from higher organic matter flux promotes a decline in oxygen concentrations below the surface. Initially, this deoxygenation may be confined to existing oxygen minimum zones and to specific semi-enclosed basins with restricted circulation. Over time, as warming continues and circulation patterns adjust, these low oxygen regions expand both vertically and horizontally. The depth range of minimum oxygen can broaden, and the upper boundary of low oxygen water can move closer to the surface, especially along continental margins where stratification is strong. In some areas, such as deeper parts of marginal seas or inland seaways connected by shallow sills, water exchange with the open ocean may be insufficient to replenish oxygen, leading to more persistent oxygen-poor conditions at depth. On the broad continental shelves that fringe parts of Pangaea, changes in sea level sediment supply and circulation further influence the distribution of oxygen. If relative sea level rises due to thermal expansion of ocean water and possible contributions from reduced ice volume, shallow seas can flood low-lying coastal areas, creating extensive but relatively poorly ventilated shelf basins. In these settings, strong stratification driven by warm, fresh surface layers and denser, more saline bottom waters can reduce vertical mixing. River plumes deliver nutrients and fine sediments that favour high productivity and rapid burial of organic matter. Bacterial decomposition of this material in the water column and in superficial sediments consumes oxygen, and if the rate of consumption exceeds the rate of replenishment, the bottom waters become hypoxic or anoxic. In more open ocean settings, the large-scale gyres of the Panthalassic Ocean respond to changed wind stress patterns as temperature gradients shift. If subtropical high-pressure zones intensify or move, the locations of upwelling and downwelling can adjust, altering the pathways by which oxygenated surface waters reach deeper levels. Some regions may experience stronger upwelling of nutrient-rich but oxygen-poor waters, reinforcing productivity and oxygen consumption near the surface. Others may experience reduced downwelling, further limiting oxygen delivery to the interior. The net result is a patchwork of changing oxygen conditions, with some basins and depth ranges maintaining adequate levels, while others trend toward more extended low oxygen states. Biological communities in the ocean experience these physical and chemical changes as altered habitat structures. Many organisms have specific temperature and oxygen ranges within which they can function. As surface waters warm, some species may track suitable conditions by shifting their geographic ranges poleward or by migrating to deeper, cooler layers. However, if oxygen-poor waters rise toward the surface and compress the vertical space in which both temperature and oxygen are suitable, the habitable zone narrows. This vertical habitat compression is particularly important for mobile animals that occupy mid-water depths and for benthic organisms on continental slopes and shelves. Where low oxygen conditions become widespread at the sea floor, many benthic communities cannot persist, and their decline leads to changes in sediment bioturbation, nutrient cycling, and the structure of food webs that span the sediment-water interface. In addition to the direct effect of temperature and oxygen on physiology, the changing environment influences the stability of stratification itself. Warmer surface waters, and in some regions enhanced freshwater input from rivers, and precipitation both tend to decrease surface density. If these effects are strong enough, they can inhibit seasonal mixing events that previously broke down the stratification and ventilated deeper layers. Without such periodic mixing, oxygen-depleted waters can persist for longer intervals between any remaining ventilation events. Over tens to hundreds of thousands of years during the main phase of end-Permian climate change, this set of feedbacks gradually shifts the oceans from a state with broadly well-ventilated deep waters and more limited oxygen minimum zones to a state where large parts of the water column, especially in certain basins and along some margins, become more extensively oxygen-poor. The detailed patterns vary between regions and remain a subject of study, but the general trend is toward warmer, more strongly stratified oceans in which oxygen is less abundant at depth and in which the balance between oxygen supply and demand is increasingly tilted toward depletion. This evolving ocean state forms the physical context in which more extreme expressions of low oxygen and related chemical changes can develop in some basins as the crisis intensifies. As the late Permian oceans warm and stratify under the influence of rising greenhouse gas levels, changes that begin at the physical scale of temperature and circulation propagate inward to affect the chemistry of seawater. One of the key processes is the exchange of carbon dioxide between the atmosphere and the ocean surface. Higher carbon dioxide levels in the air drive more of the gas into surface waters, where it reacts with water molecules to form carbonic acid. This weak acid partially dissociates into bicarbonate and hydrogen ions, and the increase in hydrogen ion concentration lowers the pH of seawater, a process known as ocean acidification. Although the change in pH may be modest in absolute terms, it has significant effects on the balance between different dissolved carbon species and on the saturation state of carbonate minerals such as calcite and aragonite. Marine organisms that build shells or skeletons from calcium carbonate draw on dissolved carbonate ions in the water. As acidification progresses, the concentration of carbonate ions declines, reducing the saturation state and making it more difficult for these organisms to precipitate and maintain their mineral structures. In shallow warm seas where many reef-building and shell-forming organisms live, this shift in carbonate chemistry can weaken existing skeletal frameworks, slow the growth of new structures, and increase the energetic cost of maintenance and repair for individual organisms. Some may still form shells under lower saturation states, but they do so at a disadvantage, and under more extreme conditions their mineral components can begin to dissolve, especially in deeper or more corrosive waters. At the same time, changes in the carbon system interact with the ongoing decline in oxygen. As stratification strengthens and deep waters become more isolated from the atmosphere, the oxygen that is present in these layers is gradually consumed by microbial respiration. Organic matter produced in surface waters sinks into the interior, where microbes use it as a source of energy and carbon, combining it with dissolved oxygen. When the rate of supply of organic matter is high and the rate of renewal of oxygen from above is low, the balance tips toward depletion. First, oxygen concentrations fall to levels that are stressful for many animals, a condition often referred to as hypoxia. If consumption continues and no fresh oxygen reaches the water, concentrations can approach zero and the water becomes anoxic, meaning that it contains no dissolved oxygen. Under anoxic conditions, different microbial communities dominate. Instead of using oxygen as an electron acceptor, microbes turn to alternative compounds such as nitrate manganese and iron oxides and sulfate. In marine environments where sulfate is abundant, sulfate-reducing bacteria become especially important. They use sulfate to oxidize organic matter, producing hydrogen sulfide as a byproduct. When hydrogen sulfide accumulates in anoxic waters, the conditions are described as eosinic, meaning that the water is both oxygen-free and sulfidic. Eosinic waters have distinct chemical and biological properties. Hydrogen sulfide is toxic to many forms of animal life because it interferes with respiratory enzymes and other critical biochemical pathways. It also reacts with dissolved metals such as iron, forming minerals like pyrite that can later be preserved in sediments. In the water column, high hydrogen sulfide concentrations can support communities of specialized microbes that use sulfide as an energy source, but they exclude most larger multicellular organisms. As late Permian warming and stratification progress, geochemical and sedimentary evidence indicates that anoxia and, in some basins, euxnia expand beyond their previous limited ranges. Black organic rich shales that form under oxygen, poor bottom waters become more widespread in some sections, and certain sulfur isotopic signatures and mineral assemblages point to intervals when sulfidic conditions reach into parts of the water column that were previously better ventilated. In shallow shelf seas where productivity is often high and circulation can be restricted by sills or basin geometry, bottom water anoxia can develop when decomposition of sinking organic matter outpaces oxygen supply. In more open ocean settings, oxygen minimum zones can intensify and extend vertically and laterally, particularly along continental margins where upwelling of nutrient-rich waters fuels high primary production. If the upper boundary of these low oxygen or euxinic waters rises close to the surface, the habitable zone for many pelagic and benthic organisms shrinks. Animals that depend on a combination of adequate oxygen and specific temperature ranges find fewer depths and regions where both conditions are met. Some may retreat to narrow bands of suitable habitat, while others face physiological stress, reduced growth, and increased mortality. Food webs that rely on a stable base of primary producers and on efficient transfer of energy through grazing and predation become unstable when key functional groups decline. Acidification also affects plankton that produce calcium carbonate shells, which play a role in the biological pump that transports carbon from the surface to the deep ocean. If these organisms decrease in abundance or produce thinner, more fragile shells, the way carbon is packaged and sinks may change, altering the depth at which organic matter and carbonate dissolve and release carbon back into the water column. This can feed back on the vertical structure of carbon and nutrient cycling, and on the location and intensity of oxygen consumption. On the seafloor, the expansion of anoxic and euxinic conditions transforms the nature of benthic habitats. In well-oxygenated settings, a diverse array of animals burrow through the upper sediment layers, mix particles and facilitate the exchange of solutes between pore waters and overlying seawater. As oxygen dwindles, these animals retreat or die out, and the sediment surface becomes dominated by microbial mats, and by chemical gradients controlled by diffusion, and by fewer, more specialized organisms. Bioturbation decreases, leading to more finely laminated sediments, that record a reduced level of animal disturbance. The loss of benthic animals that process organic matter and recycle nutrients alters the coupling between the seafloor and the water column, potentially reinforcing the persistence of low oxygen conditions by allowing more organic material to accumulate and decompose near the sediment surface. The broader carbon cycle responds to these changes in complex ways. Increased burial of organic carbon in anoxic basins can act as a long-term sink for carbon dioxide, tending to draw down atmospheric levels over geological timescales. However, this drawdown operates on timescales that may be slower than the rapid input of carbon from volcanic and contact metamorphic sources during the main phase of Siberian activity. In the shorter term, widespread anoxia and euxinia can promote the release of other reduced gases, including additional hydrogen sulfide and possibly methane from sediments, which may reach the atmosphere in some regions and further influence its composition. The balance between these sources and sinks and the timing of their operation are subjects of ongoing research, but it is clear that the late Permian Ocean shifts toward a chemically more reduced state in many basins. Within this evolving environment, the coexistence of acidifying surface waters, oxygen-poor interior layers, and in places sulfidic deep and even mid-depth waters creates a challenging set of conditions for marine life. Organisms are exposed to combinations of stresses that affect shell formation, respiration, and the stability of food supplies. The expansion of anoxia and euxinia in particular marks a deep alteration of the ocean interior, in which large volumes of water that were once part of the active oxygenated habitat space for animals are transformed into domains dominated by microbial processes and reduced chemical species. These microscale and chemical changes, though, driven by large-scale forcings at the planetary level, define the immediate environment in which individual organisms must function or fail during the height of the late Permian crisis in the seas. As physical and chemical stresses intensify in the late Permian oceans, the structure of marine ecosystems begins to change in ways that are first subtle and then increasingly severe. Communities that have been relatively stable for millions of years find their basic environmental conditions shifting beyond previously experienced ranges. Temperature, oxygen, concentration, acidity, and the presence of hydrogen sulfide interact to create combinations of stress that differ from region to region and through time. Because different groups of organisms have different tolerances and life strategies, these changes do not remove all species at once. Instead, they alter the composition, functioning and resilience of food webs in stages, with some groups declining, early others persisting longer, and a few able to survive, and even take advantage of altered conditions. In shallow tropical and subtropical shelf, seas reef-like structures and other complex benthic habitats have long been built by communities of calcifying organisms. These include various coral-like groups, sponges with robust skeletons and other invertebrates that secrete calcium carbonate and create rigid frameworks on the sea floor. Between and upon these structures, a wide variety of animals, algae, and microbes live, feeding, sheltering and reproducing in an environment with many microhabitats. As ocean acidification lowers carbonate saturation, and as warming and deoxygenation advance, these framework builders face rising energetic costs and more frequent episodes of environmental stress. Growth slows, skeletons become more vulnerable to dissolution and bioerosion, and recruitment of new individuals into the community declines. Disturbance events such as episodes of especially warm oxygen, poor or more acidic water can kill large portions of the community, leaving weakened skeletons that are more easily broken down by waves and boring organisms. Over time, the net balance between construction and destruction shifts. Instead of accumulating new carbonate structures, many reefs cease net growth or begin to lose mass. The loss of three-dimensional framework reduces habitat complexity, eliminating niches for numerous small invertebrates and fish that depend on crevices, overhangs, and stable surfaces. In settings where anoxia or euxinia periodically impinges on the seafloor, even more tolerant organisms are excluded, and the sediment surface becomes dominated by microbial mats and simpler assemblages. Beyond the reef environments on soft sediment shelves and slopes, benthic communities also change. Many late Permian seafloors are initially inhabited by diverse assemblages of burrowing and surface-dwelling animals, including bivalves, gastropods, echinoderms, and various arthropods. These organisms process organic material, oxygenate sediments, and form an important link between the water column and the substrate. As bottom waters lose oxygen, species with low tolerance for hypoxia disappear first or retreat to refuges where oxygen remains adequate. Those with higher tolerance may persist for longer, but often with reduced growth and reproduction. Bioturbation declines as fewer and simpler burrowing behaviours remain. Laminated sediments recording low levels of animal disturbance become more common. In areas where euxinic waters reach the bottom, hydrogen sulfide concentrations rise to levels that exclude almost all metazoan benthos, and only specialised microbial communities remain active at the sediment surface. These changes alter nutrient regeneration and the handling of organic matter affecting the food supply available to higher trophic levels. In the water column above, planktonic communities at the base of marine food webs respond to altered temperature, nutrient supply and chemistry. Some planktonic groups, such as calcareous phytoplankton and zooplankton with carbonate shells, experience stress from acidification, while others are more sensitive to changes in nutrient ratios or light conditions caused by shifts in mixing depth and water clarity. In regions of enhanced weathering and river input, nutrient delivery to coastal seas may increase, promoting high primary productivity and occasional blooms. These blooms can temporarily support large populations of grazers and predators, but they also produce pulses of sinking organic matter that intensify oxygen consumption at depth. In more open ocean settings where stratification limits nutrient resupply from deeper waters, productivity may decline, leading to reduced energy flow through pelagic food webs. As a result, the spatial pattern of primary production becomes more uneven, with some regions experiencing episodes of high productivity under stressed conditions and others entering more prolonged low productivity states. Nectonic animals, including many fishes and cephalopods, are particularly sensitive to the combined effects of temperature, oxygen, and prey availability. Active swimmers often have high metabolic demands and require waters with sufficient oxygen and appropriate temperatures to maintain performance. As low oxygen layers thicken and rise, the vertical habitat available to these animals constricts. If the surface waters are too warm or nutrient-poor in mid-depth, waters are too oxygen-poor, the remaining suitable habitat may be limited to narrow bands in depth or restricted geographic areas. Populations trapped in these shrinking spaces can experience crowding, increased competition, and greater vulnerability to short-term environmental fluctuations. Reproductive cycles that depend on specific temperature or oxygen conditions for spawning and larval development can be disrupted, reducing recruitment and causing population declines even before adult mortality rates rise sharply. Predatory fishes and cephalopods also suffer from changes in the abundance and distribution of their prey. If planktonic communities shift towards smaller or less nutritious forms, or if intermediate trophic levels decline the energy available to top predators falls. Some species may adjust their diets or shift ranges to locate remaining productive regions, but others are limited by physiological or behavioral constraints and cannot readily adapt to the new conditions. Over time, pelagic food webs in some basins lose complexity with fewer trophic levels and a dominance of opportunistic species that can tolerate variable or extreme conditions. The fossil record across the Permian Triassic boundary documents these ecological changes in terms of losses in diversity, abundance, and ecological roles. Many groups that have been abundant and widespread throughout earlier Paleozoic and Permian seas decline sharply or disappear entirely. Among benthic invertebrates, certain brachiopod groups, many echinoderms and trilobites, reach their final extinction. Reef-building coral-like organisms suffer near total collapse. Ammonoid cephalopods, which have been diverse and common, experience a major reduction in diversity, with only a small fraction of lineages surviving into the earliest Triassic. Conodonts and other small-toothed vertebrate-like organisms that occupy mid-trophic levels in some marine systems also show turnover patterns consistent with significant environmental stress. Bony fishes and cartilaginous fishes experience selective losses, with some clades more affected than others, reflecting differences in habitat preference and physiology. The pattern of extinction and survival is not random. Groups with particular combinations of traits, such as high dependence on well-oxygenated environments, specialized ecological roles, narrow geographic ranges, or heavy reliance on carbonate skeletal structures, tend to fare worse. Conversely, taxa that are more tolerant of low oxygen temperature fluctuations and changes in salinity or pH, or that have broader geographic and ecological distributions, are more likely to persist. Small generalist feeders with simple life histories and flexible diets often survive where larger, more specialized organisms do not. This selectivity means that the end Permian crisis not only reduces overall diversity, but also reshapes the functional structure of marine ecosystems, favouring opportunistic and stress-tolerant forms over more specialised and tightly integrated communities. As extinctions accumulate over tens to hundreds of thousands of years, the cumulative impact on marine ecosystems becomes profound. In many regions, the once complex webs of interaction among reef builders, grazers, predators and decomposers give way to simpler systems dominated by a limited set of survivors and by microbial communities that exploit the new chemical environment. The loss of key engineering species removes physical structures and feedbacks that previously stabilized habitats. Nutrient cycles operate differently when benthic animals are scarce, and when microbial processes in anoxic and euxinic waters dominate the breakdown of organic matter. Even where some parts of the food web remain intact, they are embedded in an ocean whose physical and chemical state has shifted markedly from the earlier late Permian baseline. The combination of acidification warming deoxygenation and in some basins widespread euxinia thus drives a long stepwise erosion of marine ecosystem complexity that culminates in the largest recorded loss of marine genera in the Phanerozoic, leaving the earliest Triassic seas sparsely populated and structured very differently from those that existed just before the crisis began. On land, the same forces that alter the late Permian atmosphere and oceans begin to reshape climates, soils, and plant communities across the supercontinent. Rising greenhouse gas levels and changing circulation patterns warm the continental surfaces and modify rainfall in ways that place increasing stress on vegetation and the ground it covers. Interior regions of Pangaea, already prone to strong seasonal contrasts and limited moisture, experience hotter summers and in many areas more prolonged dry intervals. Coastal and monsoon-influenced regions may receive intense rainfall during wet seasons, but also face hotter conditions and at times more irregular delivery of water through the year. The result is not a uniform shift toward either wetter or drier conditions everywhere, but a general increase in climatic extremes. Some areas oscillate between episodes of heavy rain and extended drought, while others trend towards sustained aridity. These changes in temperature and moisture interact with the chemistry of the atmosphere. Volcanic emissions from the Siberian flood basalts include sulfur-bearing gases that can oxidize in the atmosphere to form sulfuric acid aerosols. When these aerosols mix with water vapor and fall as precipitation, they contribute to acid rain. The degree and geographic spread of acidification in rainfall remain subjects of uncertainty, but even moderate increases in acidity can damage plant tissues, leach nutrients from soils, and mobilize toxic metals. Repeated deposition of acidic precipitation over years to centuries reduces the buffering capacity of soils, especially where they are thin or derive from parent materials with low carbonate content. Nutrient cations such as calcium and magnesium can be washed out, while aluminum and other potentially harmful elements are released in more soluble forms, further stressing root systems. At the same time, possible damage to the ozone layer by halogen emissions may increase the flux of ultraviolet radiation that reaches the surface in some regions and seasons. Plants exposed to higher levels of ultraviolet radiation can suffer from impaired photosynthesis, DNA damage, and reduced growth, particularly in sensitive tissues such as young leaves and reproductive structures. The extent of this effect and its contribution relative to other stresses are still debated, but it represents an additional potential burden on vegetation already coping with heat, drought, and altered soil chemistry. The combined influence of hotter temperatures, altered rainfall, acid deposition, and possible ultraviolet changes modifies the geographic ranges and health of plant communities. In humid low-latitude and mid-latitude belts, forests that once covered large areas begin to fragment. Some regions that previously supported dense stands of seed ferns, conifers, and other gymnosperms transition toward more open woodlands and scrub. In the southern parts of Pangaea, where extensive coal-forming wetlands have existed, during earlier phases of the Permian, evidence from the sedimentary record indicates a reduction or disappearance of peat-forming environments around the time of the crisis, a feature sometimes referred to as a coal gap. This suggests that the combination of hydrological change and temperature stress makes it difficult for waterlogged peat, accumulating ecosystems to persist. Without persistent high water tables and stable, cool, moist microclimates, the balance between plant production and decay shifts and organic matter that once would have accumulated as peat decomposes more fully. In other regions, especially continental interiors and rain shadow zones, increasing aridity and heat promote the spread of more xeric vegetation and ultimately of sparsely vegetated or barren landscapes. Soils in these areas lose organic matter and structure as plant cover thins, exposing them to erosion by wind and occasional intense rainfall. Surfaces that were once stabilized by roots become more easily stripped of fine material, leaving behind coarser lags and forming desert pavements or dune fields. Dust generated in these environments can be transported by winds over long distances, affecting radiation balance and depositing mineral particles in distant basins and oceans. The loss of plant cover also changes local water cycles. With fewer roots and less canopy, more rainwater runs off quickly, rather than infiltrating, producing flash floods in some settings, and further reducing the recharge of soil moisture and groundwater. Plant groups respond differently to these stresses. Some conifers and other gymnosperms with deep roots and drought-resistant traits can survive in drier, hotter conditions, especially if they occupy refuges along rivers in uplands, with reliable moisture or near coastlines where humidity remains higher. Seed ferns and other plants adapted to more stable humid climates often fare worse, retreating to restricted pockets where conditions remain favourable. In parts of what is now South China and other equatorial to subtropical regions, large members of groups such as the gigantopterids, which previously formed significant components of rainforest-like vegetation, decline or disappear from the record as late Permian conditions give way to those at the boundary. Understory plants and ground-level vegetation also change in composition. Ferns and other spore-bearing plants, which can disperse rapidly and colonize disturbed ground, may briefly expand in disturbed areas following dieback of woody vegetation, as suggested in some pollen and spore records that show pulses of fern spores after major vegetation loss. These spikes indicate episodes when forest canopies open widely, exposing soils to light and allowing opportunistic plants to spread. However, if harsh conditions persist or intensify, even these colonizers may not maintain continuous cover, and the landscape can shift between short-lived vegetated phases and more prolonged open eroding states. Fires form another pathway by which late Permian environmental change affects land surfaces and plants. Warmer temperatures, drier seasons, and more frequent lightning in some regions can increase the frequency and extent of wildfires. Charcoal and other fire-related indicators in some sedimentary sequences suggest that fires play a significant role in restructuring vegetation during parts of this interval, although the timing and global extent of increased fire activity remain under investigation. Fires remove biomass-alter soil properties and change the composition of plant communities by favouring species that can re-sprout or rapidly colonize burned areas. Repeated burning in a regime of increasing aridity can trap some landscapes in states with low woody cover and high exposure, making it more difficult for closed forests to re-establish. As soils degrade and vegetation recedes, feedbacks develop that reinforce the stresses. Reduced plant cover means less evapotranspiration, which can decrease local humidity, and cloud formation, further limiting rainfall in some areas. Less organic matter entering the soil weakens its structure and reduces its ability to retain water and nutrients. Erosion carries fine material and nutrients away, depositing them in basins where they may briefly support productivity, but ultimately lead to sediment accumulation that can bury low-lying habitats. On slopes, mass wasting and gullying become more common, reshaping topography on smaller scales. The cumulative effect is a patchwork of land surfaces, some still vegetated and relatively stable, others deeply altered and more prone to further degradation. These terrestrial changes do not occur everywhere at exactly the same time or with the same intensity. Some regions retain forests and relatively moist climates, through much of the crisis serving as refuges for plant lineages that later participate in recovery. Others, particularly in more central parts of Pangaea, or in regions directly affected by volcanic deposits and ash falls, experience rapid and severe transformation. The fossil record of plant macrofossils, pollen and spores shows both abrupt and more gradual shifts, reflecting local conditions and the complex interplay of climate, volcanic forcing and basin history. Despite this variability, the broad pattern indicates that late Permian and earliest Triassic land surfaces see a general decline in forested area, a simplification of vegetation structure, and a move toward more open, stressed landscapes. Within this evolving mosaic, soils lose some of the protective and stabilizing influence of continuous plant cover and organic input. Weathering regimes shift as exposed mineral surfaces interact more directly with rainfall and atmospheric inputs. The loss of extensive long-lived root systems reduces the capacity of soils to store carbon and water. Together, these changes in climate, soils, and plant communities reshape the physical and biological foundations of terrestrial environments, creating conditions that will strongly influence how land-dwelling animals respond as the crisis progresses. As late Permian environmental stresses intensify on land terrestrial invertebrates and vertebrates, respond within the altered climates and degraded plant communities that have developed across much of the supercontinent. Animals depend on the structure and productivity of vegetation for shelter food and the stability of soils and microhabitats, so the decline and fragmentation of forests, the spread of more open and arid landscapes, and the increased frequency of disturbance events such as fire and flooding all feed into the pressures that land faunas experience. These pressures arise in different combinations in different regions, including heat stress during hotter summers, water stress during longer or more irregular dry seasons, reduced availability of plant material for herbivores, and less predictable prey populations for predators. Invertebrates feel these changes both directly and indirectly. Insects and other arthropods are sensitive to temperature, moisture, and the quality and abundance of host plants. As forest canopies thin and retreat, insects that depend on particular tree or understory species lose habitat and food sources. Some species can track their preferred conditions into refuges where suitable vegetation remains, but others with narrow host ranges or limited dispersal ability cannot easily shift. In more open and arid environments, insect communities tend to be dominated by forms that tolerate heat desiccation and highly seasonal resource availability. The fossil record based on insect body fossils and on traces such as feeding marks in leaves and coprolites suggests that late Permian insect diversity decreases markedly around the time of the crisis, with many lineages disappearing and others contracting their ranges. This loss is notable because throughout most of the fossil record, insects have shown high resilience to environmental change. The magnitude of the reduction in insect diversity during the late Permian and earliest Triassic stands out as the most severe known extinction event for terrestrial arthropods in the Phanerozoic. Soil and litter-dwelling invertebrates, including arthropods, annelids, and other groups, also respond to changes in vegetation and soil chemistry. As leaf litter inputs decline and become more irregular, and as soils acidify or dry, the communities of decomposers and detritivores that break down organic matter and recycle nutrients change in composition and abundance. These organisms play a key role in maintaining soil structure and fertility, so their decline or alteration feeds back into plant stress and the capacity of soils to support complex root systems. The reduction in fine root networks from stressed vegetation further alters soil pore structure and gas exchange, affecting the microhabitats available to small invertebrates. The combined result in many regions is a simplification of invertebrate communities and a reduction in the density and diversity of soil and litter animals. Among vertebrates, freshwater and semi-aquatic groups such as many amphibians occupy habitats that are particularly sensitive to climate and hydrological change. Amphibians generally rely on moist environments and often on water bodies for reproduction. As climates become more seasonal or arid, wetlands shrink or become more ephemeral, streams shift from perennial to intermittent flow, and lakes experience greater fluctuations in level temperature and chemistry. Acidification from atmospheric inputs and from altered catchment soils can further stress amphibian eggs and larvae, which are exposed directly to water chemistry. In the late Permian, diverse groups of amphibian-grade tetrapods, including large temnospondyls, inhabit rivers, lakes, and coastal lowlands. The fossil record shows that many of these lineages decline sharply at or near the Permian-Triassic boundary, with only a subset of forms surviving into the earliest Triassic. Survivors often appear to be those that are smaller in body size, have flexible life histories that can cope with variable water availability, or occupy refuges in regions where aquatic habitats remain relatively stable. On the drier parts of the landscape, early reptiles and synapsids experience the consequences of vegetation loss and climate change through altered food webs and habitat structure. Herbivorous vertebrates depend directly on the quantity and quality of plant biomass. As forested areas contract, and as plant communities shift toward more drought-tolerant but less productive forms, the carrying capacity of many landscapes for large herbivores decreases. Animals that once fed in dense woodlands or on lush undergrowth now encounter more sparse resources spread over larger areas. Some can adapt by broadening their diet to include tougher, more fibrous plant material, by ranging over wider territories, or by shifting activity patterns to avoid the hottest parts of the day. Others, especially large specialized herbivores, have less flexibility. Fossil assemblages from late Permian and earliest Triassic terrestrial deposits show a reduction in the diversity and abundance of several major herbivorous clades, including some large synapsid and parareptile groups. Carnivorous and omnivorous vertebrates feel the impact of these changes strongly because they sit at higher trophic levels. In a collapsing food web, energy losses at the base propagate upward. As primary productivity declines, and as herbivore populations shrink or become more patchily distributed, predators face reduced and less reliable prey supplies. Large apex predators, which require significant amounts of food and often occupy large territories, are particularly vulnerable to such reductions. In the late Permian, many land ecosystems are structured around large carnivorous synapsids and reptiles that hunt substantial herbivores and smaller prey. As conditions deteriorate, these apex predators decline in diversity and abundance, with entire clades disappearing in some regions by the time of the boundary. The fossil record indicates that several major lineages of large carnivorous therapsids, for example, do not persist into the earliest Triassic in many areas. Smaller vertebrates, including small cynodonts, therocephalians, and early diapsids, show somewhat higher survival rates consistent with the general pattern that species with small body size generalist diets and flexible behaviors fare better in times of environmental stress. Body size reduction or dwarfing is a common response in some lineages, as smaller individuals require less food and can reproduce more quickly under resource-limited conditions. The structure of terrestrial vertebrate communities changes not only in terms of which taxa are present, but also in terms of their spatial distribution. As climates become more heterogeneous, and as some regions become inhospitable, animals track shifting suitable conditions across the landscape. This can lead to range contractions into refugia, where climates remain milder or more stable, such as coastal zones, upland areas with reliable water, or regions buffered by local geographic features. In some basins, fossil assemblages show evidence for faunal turnover, as earlier late Permian communities are replaced by new early Triassic assemblages dominated by a few opportunistic species. One well-studied example is the rise of small burrowing or semi-fossorial herbivores, such as Lystrosaurus in certain southern Pangaean regions, where this genus comes to dominate vertebrate assemblages in terms of abundance. Although this dominance is more fully developed in the earliest Triassic, its roots lie in the selective survival of particular morphologies and life strategies through the crisis interval. Extinction selectivity in terrestrial vertebrates appears to be influenced by several factors. Dependence on stable productive forests makes some large herbivores especially vulnerable to vegetation collapse. Reliance on permanent water bodies exposes many amphibians and some reptile groups to risk when hydrological regimes become more variable. High metabolic demands and large body size increase the sensitivity of predators to declines in prey. In contrast, traits that favor survival include small-size burrowing or shelter-seeking behaviors that mitigate temperature and moisture extremes, broad diets that allow feeding on a wide range of plant or animal matter, and reproductive strategies that enable rapid population recovery when conditions temporarily improve. These patterns are inferred from the differential survival of clades and from changes in body size distributions and functional traits across the boundary. Over the full duration of the crisis, which spans on the order of several 100,000 to perhaps around 1 million years when viewed at fine resolution, the cumulative effect on terrestrial vertebrate and invertebrate faunas is a marked reduction in diversity and a simplification of community structure. Many late Permian ecosystems, once characterized by multi-layered plant canopies, diverse invertebrate assemblages, and complex vertebrate food webs are replaced by early Triassic landscapes, in which a smaller number of species occupy a wider range of ecological roles. The physical environment of hotter, more arid, and more erosion-prone surfaces, combined with stressed plant communities and altered soils, shapes this transition. The declines on land thus parallel in many ways those in the oceans, although the relative severity and timing differ among groups and regions. By the end of the main extinction interval, terrestrial communities in many parts of Pangaea are dominated by a limited set of generalist survivors, embedded in landscapes that bear the imprint of significant climatic and environmental disruption. The record of the Great Dying is preserved not in direct observation, but in the layered rock sediments and chemical signatures that span the Permian-Triassic boundary. These strata, exposed today in cliffs, road cuts, quarry faces and drill cores on several continents, form the inner line of evidence from which the timing, duration, and nature of the crisis are reconstructed. Although each basin has its own local history, common patterns appear when records from marine and terrestrial environments are examined together. In many marine successions, late Permian rocks consist of thick packages of limestone, dolostone, and other carbonate-rich sediments laid down on continental shelves and slopes. These units often contain abundant fossils of shells' skeletal fragments and reef-building organisms reflecting productive and diverse shallow seas. Bedding features such as cross-lamination bioturbated layers and burrow structures show that bottom waters are oxygenated enough to support active benthic life. Above these layers, a distinctive interval marks the transition into earliest Triassic strata. In some sections, this boundary zone is relatively thin, only a few tens of centimeters thick. In others, it is spread over thicker intervals. Within it, several changes occur in parallel. Fossil assemblages shift abruptly, with many late Permian taxa disappearing at or just below a particular bed, and a simpler earliest Triassic fauna appearing above. Sedimentary structures indicating intense bioturbation become rare or absent and laminated. Fine-grained sediments accumulate with few signs of large burrowing animals. In certain basins, especially those that were deeper or more restricted, black organic rich shales appear or become more prevalent around this level, consistent with deposition under oxygen-poor bottom waters. Conodonts, small tooth-like elements from eel-shaped vertebrates, provide a finely resolved biostratigraphic tool in many marine sections. Their rapid evolutionary turnover and widespread distribution allow the definition of zones based on characteristic species. Across the Permian Triassic boundary, conodont assemblages show a marked turnover, with late Permian species disappearing and earliest Triassic forms appearing in a relatively narrow stratigraphic interval. This pattern, combined with similar shifts in other fossil groups, supports the interpretation that major changes in marine life occur over a geologically brief span, rather than being spread evenly over many millions of years. Chemical analyses of these boundary strata add another layer of information. One of the most studied signals is the ratio of stable carbon isotopes in carbonate minerals and organic matter. Carbon has isotopes with different masses, and biological and geological processes can prefer one isotope over another, leaving a record in the isotopic composition of sediments. In many marine and terrestrial sections, the carbon isotope record shows a pronounced negative excursion across the boundary, meaning that the ratio of the heavier isotope to the lighter isotope declines over this interval. This excursion can be several parts per thousand in magnitude, and is often associated with the main pulse of extinction and environmental change. The negative shift suggests a rapid addition of isotopically light carbon to the ocean atmosphere system, a pattern consistent with large-scale input from volcanic emissions, the release of carbon from heated sediments or other sources related to the processes already acting in the late Permian. The precise partitioning among these sources is still debated, but the broad signal of a large, relatively rapid carbon cycle disturbance is widely recognized. Other isotopic systems provide complementary information. Oxygen isotopes in marine carbonates carry a combined signal of temperature and the isotopic composition of seawater, which can be influenced by factors such as ice volume and evaporation patterns. Across the boundary, some records suggest warming in surface and shallow subsurface waters, in line with independent lines of evidence for greenhouse gas-driven temperature rise, though local conditions and diagenesis complicate the picture. Sulfur and strontium isotopes, which respond to changes in weathering volcanism and the extent of anoxic and eutxinic conditions, also show shifts near the boundary in many sections, indicating altered redox conditions and global-scale changes in the cycling of these elements. Sedimentary facies changes across the boundary provide further context. In some shallow marine settings, thick late Permian carbonate platforms with well-developed reefs and shoal complexes give way to thinner, more uniform beds of macritic limestone or mixed carbonate siliciclastic sediments lacking large skeletal frameworks. The disappearance of complex reef faces and their replacement by simpler deposits is consistent with the ecological collapse described earlier. In deeper settings, the onset or expansion of laminated black shales with high organic carbon content points to broader and more persistent anoxia in the water column. Fine lamination absence of burrows, and the presence of certain mineral and fossil assemblages that form under low oxygen conditions all support this interpretation. On land, boundary successions are more variable due to differences in basin type, sediment supply and exposure, but some recurring themes can be recognized. In several regions, late Permian fluvial and floodplain deposits that contain diverse plant fossils and vertebrate assemblages are overlain by beds that record a shift toward more arid erosion-dominated conditions. Coals and peats that formed in wetland environments become rare or absent over an extended interval of early Triassic time corresponding to the coal gap. Instead, red bed sediments indicative of oxidizing conditions and more open, seasonally dry landscapes dominate in many basins. Paleosols or fossil soils show changes in structure and composition consistent with increased aridity, reduced organic matter, and more intense weathering. Pollen and spore records extracted from these strata show shifts in plant communities. In some successions, diverse late Permian assemblages with contributions from various gymnosperm and seed fern groups give way to earliest Triassic assemblages dominated by a narrower range of pollen types. Short-lived spikes in spores of certain opportunistic plants such as ferns have been interpreted in some sections as evidence for temporary proliferation of disturbance-adapted vegetation following episodes of forest dieback, although the extent and universality of such signals remain subjects of study. Combined with macrofossil evidence, these palynological records support the inference of widespread vegetation loss and restructuring around the boundary. Radiometric dating techniques, particularly those based on the decay of uranium to lead in zircons within volcanic ash layers, help anchor these stratigraphic and fossil patterns in absolute time. In a few marine and terrestrial sections, thin ash beds near the Permian-Triassic boundary contain zircons that can be dated with high precision. These dates, when tied to the biostratigraphic and chemostratigraphic markers, indicate that the main extinction interval and associated environmental changes occur over a relatively short span in geological terms, on the order of a few 100,000 years or less, even if some stresses and smaller scale events precede and follow this main phase. The exact duration and structure, including whether the extinction proceeds in one dominant pulse or several phases, varies among datasets and remains an area of active research. But the combination of fossil turnover, isotopic excursions and sedimentological shifts points to a concentrated crisis rather than a diffuse, slowly unfolding decline. Uncertainties arise from several sources. Local depositional gaps where sediment is not preserved or is later eroded can remove parts of the record and make continuous sequences rare. Diagenetic alteration in which original mineral and chemical signatures are modified during burial and fluid flow can blur or overprint primary signals, especially in older and deeply buried rocks. Lateral facies changes where environments shift across a basin mean that a single section may not capture the full range of conditions or biotic responses present at a given time. To address these issues, researchers compare multiple sections from different paleogeographic settings, both marine and terrestrial, and use a combination of stratigraphic tools to align them. When this broader synthesis is carried out, the picture that emerges is one of a global event recorded in many places by a combination of abrupt fossil disappearances, distinctive geochemical anomalies, and changes in sedimentary faces and structures. The Permian-Triassic boundary thus appears as a recognizable horizon or interval in the rock record characterized by the loss of many long-standing taxa, the onset of new, simpler communities, and chemical evidence of major perturbations in the carbon and sulfur cycles, oxygen levels, and climate. These signals form the basis for inferring the scale, rapidity, and environmental context of the Great Dying, and they provide the framework within which hypotheses about its causes and mechanisms are developed and tested. The fossil record of the Permian-Triassic boundary not only documents losses but also reveals patterns in which organisms persist, how communities reorganize, and which ecological roles vanish or continue into the earliest Triassic. By examining assemblages from many regions and environments, it becomes possible to see that the crisis is not a uniform removal of life, but a selective event that reshapes the structure of ecosystems. This selectivity is expressed in the differential survival of taxa with particular body plans, metabolic strategies, habitat preferences, and geographic distributions. In the marine realm, reefs provide one of the clearest examples. Late Permian reefs are built by a range of calcifying organisms, including diverse sponges, coral-like groups, and other skeleton-forming invertebrates that create massive rigid frameworks. These structures support rich associated faunas of mollusks, echinoderms, arthropods, and small vertebrates. At and just above the boundary, these framework-building communities disappear almost everywhere that continuous sections are preserved. In many places, there is a gap of several million years before large rigid reefs reappear, During this interval, shallow marine substrates are dominated by microbialites and other low-relief carbonate structures formed by microbial mats and thin crusts. The widespread occurrence of such microbial deposits in earliest Triassic shallow marine strata indicates that in the absence of complex metazoan reef, builders' microbes expand into ecological space and become the primary agents of carbonate binding and accumulation. The transition from skeletal reefs to microbialites therefore marks a clear shift in the identity of key ecosystem engineers and in the physical architecture of shallow marine habitats. Within non-reef benthic communities, the pattern of survival varies among major groups. Many late Permian brachiopods, particularly those with thick shells and specialized attachment habits, decline sharply and do not reappear. In contrast, some bivalve mollusks, especially forms that can infaunally burrow into sediments or that have robust simple shells, survive and diversify in earliest Triassic seas. This suggests that traits such as flexible feeding strategies, ability to tolerate variable oxygen and salinity conditions, and capacity to exploit softer substrates confer advantages under stressed conditions. Similarly, among gastropods, small generalist species appear more likely to persist than larger, more specialized forms. Echinoderms show strong selectivity as well. Crinoids and other stalked or attached groups dependent on stable, well-oxygenated substrates and moderate energy flow suffer severe losses, with only a subset of lineages surviving and later radiating. Sea urchins and related groups, some of which can tolerate more varied conditions and occupy a wide range of benthic settings, show different patterns depending on local environments, but overall decline less completely than more sensitive counterparts. Trilobites, which have already declined through the late Paleozoic, do not survive the boundary. Their complete disappearance at this time indicates that any remaining lineages are unable to cope with the combined stresses of chemical change, deoxygenation, and habitat disruption, and it marks the final end of a clade that has persisted for hundreds of millions of years. Mobile nectonic groups also exhibit distinct survival patterns. Ammonoid cephalopods, which are diverse and abundant in many late Permian assemblages, experience a severe but not total extinction. Only a small fraction of species and perhaps a few family-level lineages persist into the earliest Triassic, where they initially show low diversity and relatively simple morphologies. These survivors often possess traits such as small shell size, simple sutures, and perhaps broad geographic ranges, although the exact combination of beneficial traits is still under study. In contrast, entire subgroups such as some goniotitic forms disappear. Through the early Triassic, the surviving ammonoids diversify rapidly, but their starting point is a reduced bottlenecked fauna. Conodonts, as small vertebrate-like animals inhabiting the water column, show rapid taxonomic turnover at the boundary, with many late Permian species replaced by a simpler suite of earliest Triassic forms. The morphology of their elements and their distribution across faces provide clues about the conditions under which they live and about water column structure. The continued presence of conodonts in earliest Triassic strata indicates that at least some planktivorous and small predator niches remain occupied in the aftermath, even though the broader ecosystem is reduced. Cartilaginous and bony fishes show more complex patterns that are still being clarified as new fossils are found. Some groups decline strongly or disappear from particular regions, especially those that favor reef or shelf. Environments that are heavily affected by anoxia and habitat loss. Others persist in basins where conditions remain more favorable, or in habitats that act as refugia, such as certain near-shore or high-latitude areas. Generalist feeders' small body sizes and tolerance for variable oxygen and salinity likely aid survival. The fossil record suggests that although fish diversity declines, fishes as a whole do not experience complete collapse, and they continue to play important roles in the simplified earliest Triassic food webs. The distribution of survivors and victims also varies geographically. Some high-latitude or deeper water settings where temperature changes and acidification may be less extreme at the surface, or where different circulation patterns apply, appear to act as refuges for certain taxa. Likewise, regions less directly impacted by the most intense expressions of Euxinia in the water column may retain more continuous benthic communities. These refugial areas can later serve as sources for recolonization, as conditions slowly improve in more strongly affected basins. However, the patchiness of preservation and the limited number of well-studied sections mean that such patterns must be interpreted cautiously. On-land survival patterns among plants and vertebrates echo some of the marine selectivity. Plant fossil and pollen records indicate that groups with broad ecological tolerances An efficient dispersal, such as some conifers and pteridophytes, withstand the crisis better than large moisture-dependent rainforest components, such as certain seed ferns and gigantopterids. In many basins, earliest Triassic floras are dominated by a smaller number of gymnosperm and opportunistic spore-bearing species relative to late Permian assemblages. This does not imply that all late Permian plant diversity disappears. Instead, many lineages retreat to refuges or persist at low abundance in regions where moisture and temperature conditions remain within tolerable limits. Over time, some of these survivors expand again, but in the immediate aftermath, the land-plant component of ecosystems is simplified with a functional bias toward drought and stress-tolerant forms. Among terrestrial vertebrates, small body size fossorial or semi-fossorial habits and generalist diets stand out as features associated with survival. Cynodonts and therocephalians that survive into the earliest Triassic often belong to lineages characterized by relatively small skulls and bodies interpreted to indicate reduced energy demands. Burrowing or denning behaviors inferred from limb morphology, and sometimes from trace fossils, may provide protection from temperature extremes, desiccation, and surface fires. Herbivorous synapsids that persist are frequently medium to small animals, capable of feeding on a variety of plant parts, including root stems and tough leaves, rather than specializing on a specific forest type. Early diapsid reptiles that survive or begin to diversify in the earliest Triassic include forms that occupy a range of ecological roles, from small insectivores to medium-sized predators, again often with features suggesting ecological flexibility. Large specialized predators and herbivores decline more thoroughly. The absence or rarity of many late Permian apex predators in earliest Triassic faunas indicates that high trophic level roles are largely vacant or filled by new smaller forms. This reorganization of trophic structure is reflected in body size distributions, which shift towards smaller sizes in many assemblages. The dominance of a few taxa, such as Lystrosaurus, in some southern Pangaean vertebrate communities illustrates how a single successful generalist can occupy much of the available herbivore biomass under stressed conditions. Although these extreme dominances may be local or regional phenomena, they highlight the simplification and reweighting of terrestrial food webs. The patterns of survival and extinction across marine and terrestrial realms together underline that the Great Dying is not simply a random pruning of diversity. Groups that are physiologically sensitive to heat, low oxygen acidification, or toxic substances that depend on stable, highly structured habitats, or that have limited dispersal ability generally fare poorly. Groups that tolerate a wide range of environmental conditions that can exploit disturbed or variable habitats, that have broad geographic distributions, and that often have small body size and rapid life cycles more often persist. These differences give researchers insight into the environmental stresses at work, since the combination of traits that correlate with survival points back to the kinds of conditions to which organisms must adapt. At the same time, the selectivity of survival shapes the trajectory of recovery. The early Triassic biosphere inherits its starting set of species from this narrowed pool of survivors. The absence of many former framework builders, apex predators, and other key functional groups means that recovery begins from a different ecological baseline than the late Permian one. Microbial communities play larger roles in organizing sediments and cycling nutrients. Small generalist animals dominate many food webs, and structurally complex habitats are rare. In this way, the fossil record across the Permian-Triassic boundary not only records the magnitude of loss, but also sets out the pattern of survivors that will govern the long, uneven rebuilding of ecosystems in the earliest Triassic oceans and on land. In the earliest Triassic, after the main extinction interval has passed, the oceans of Earth continue to bear the imprint of the late Permian crisis. The physical and chemical changes that developed during the peak of volcanic forcing and environmental disruption do not disappear quickly. Instead, they persist, and in some respects intensify for an extended period, creating a world in which surviving organisms must operate within a fundamentally altered marine environment. Sea surface temperatures in many low to mid-latitude regions remain elevated relative to late Permian baselines, supported by the continuing presence of high greenhouse gas concentrations in the atmosphere and by the thermal inertia of the ocean itself. Stratification of the water column remains strong in many basins, limiting vertical mixing and the ventilation of deeper layers. Oxygen poor, and in some regions, euxinic waters continue to occupy large volumes of the ocean interior, particularly along continental margins and in semi-enclosed basins. The spatial extent and intensity of these low oxygen zones may fluctuate with regional climate productivity and circulation changes, but as a whole, the earliest Triassic ocean is less well oxygenated than its late Permian predecessor. In such a setting, many of the structurally complex ecosystems that once occupied shallow seas are absent or greatly reduced. Instead, microbial communities expand into ecological space that previously belonged to metazoan reef builders and other framework-constructing organisms. On carbonate platforms and in other shallow settings where conditions still allow carbonate precipitation, microbial mats form cohesive films on the sea floor. These mats, composed of bacteria and other microbes embedded in extracellular material, trap and bind sediment grains, stabilize surfaces and promote the precipitation of carbonate minerals within and around their structures. Over time, repeated growth trapping of particles and mineralization build up layered domal columnar or irregular structures that when lithified are known as microbialites. In the earliest Triassic, these microbialites become widespread in many shallow marine basins, appearing where late Permian reefs have disappeared, or where only thin remnants of skeletal frameworks remain. The morphology of these microbial deposits varies depending on local conditions such as water depth, energy levels, sediment supply, and the nature of the microbial communities. Some form broad, low-relief pavements with thin lamination, while others build more pronounced mounds or columns that rise a metre or more above the surrounding seafloor. Despite this variation, a common theme is the dominance of microbial processes in the construction and maintenance of seafloor structures. In contrast to late Permian reefs, which host diverse, densely packed assemblages of invertebrates and other metazoans, earliest Triassic microbialite systems typically support simpler associated faunas. In some sections, shells of bivalves, gastropods, and small echinoderms are found within or on top of microbialites, indicating that certain invertebrates can exploit these habitats as substrates or refuges. However, the overall diversity and abundance of metazoan reef dwellers are low compared with earlier intervals. The spaces between microbial structures are often filled with fine sediment rather than the rich bioturbated deposits characteristic of healthy reef ecosystems. This change reflects both the reduced level of oxygen in bottom waters, which restricts the activity of many animals, and the lingering stresses of temperature and chemistry that limit the range of species able to persist. In the water column above, plankton communities form the base of earliest Triassic marine food webs. Evidence from microfossils suggests that some planktonic groups, including certain algae and small skeletal producers, survive the boundary and continue to function, although often with reduced diversity. Other groups show strong declines or delayed recovery. The altered nutrient regime of the earliest Triassic ocean, shaped by intensified weathering on land, ongoing volcanic inputs, and changes in circulation, can lead to episodic blooms in some regions and low productivity in others. Where nutrient-rich waters reach the surface, microbial and algal blooms may develop, fueling short-term increases in food supply for grazers, but also reinforcing deoxygenation at depth when organic matter sinks and decomposes. In more stratified nutrient-limited regions, primary production remains low, and the overall energy throughput in the ecosystem is constrained. Nectonic animals, including survivors among fishes and cephalopods, navigate this patchy and stressed environment. Their distribution is often restricted to depth ranges where oxygen and temperature conditions are still within tolerable limits, a zone that can be relatively narrow in strongly stratified basins. Some earliest Triassic fish assemblages are dominated by small generalist species that feed on a variety of planktonic and benthic prey. Large specialized predators are rare or absent in many records, consistent with the idea that higher trophic levels are difficult to sustain in food webs with limited primary productivity and frequent environmental disturbances. Ammonoid cephalopods, though reduced in diversity, appear in earliest Triassic strata with simple shell forms, and their presence indicates that at least some pelagic predator and scavenger niches remain occupied. However, their numbers and variety are small compared with the late Permian faunas, and their geographic distribution suggests that they may be constrained to particular basins or depth zones that act as refugia. The structure of earliest Triassic marine ecosystems thus tends toward low diversity dominance by a few successful survivor groups and a greater role for microbial processes in both benthic and pelagic realms. In many shallow seas, microbialites and thin shelly faunas form the main visible components of benthic communities. In deeper settings, laminated organic-rich sediments continue to accumulate under oxygen-poor waters, with few, if any, burrowing animals. The scarcity of large, complex reef frameworks and of densely populated benthic assemblages means that habitats with high structural complexity are rare. This has consequences for the ways in which energy and materials flow through the system. Without extensive bioturbation, sediment layers remain more sharply stratified, with chemical gradients controlled primarily by diffusion and microbial metabolism. Nutrient regeneration may be slower or more localized, and the coupling between seafloor processes and water column productivity is changed. Despite the overall stress state of the oceans, earliest Triassic time is not static. Over hundreds of thousands to a few million years, volcanic activity in the Siberian province declines from its peak, and the rate of new greenhouse gas input into the atmosphere eventually decreases. At the same time, the carbon cycle continues to operate through weathering of exposed volcanic and continental rocks, burial of organic matter in marine and terrestrial sediments, and the biological uptake and release of carbon in surviving ecosystems. Chemical weathering of fresh basalt surfaces and uplifted terrains draws down carbon dioxide from the atmosphere, although this drawdown acts on timescales that are long compared with individual generations of organisms. As volcanic forcing wanes and as carbon removal processes persist, greenhouse gas concentrations may begin to stabilize or decline slowly. Even small changes in the balance between input and removal can over extended intervals allow the climate system to move gradually toward a new equilibrium that is still warm but less extreme than conditions at the peak of the crisis. In parallel, the extent and intensity of ocean anoxia and euxenia can change as circulation patterns adjust and as the supply of organic matter to depth varies. Some basins may experience partial reoxygenation of intermediate and deep waters, especially where climate-driven changes in wind patterns, temperature gradients, or freshwater input alter the loci and strength of deep water formation. In other areas, low oxygen conditions persist for longer, maintaining stressed habitats well into the earliest Triassic. This spatial and temporal variability means that the path of ecological adjustment is uneven. Certain regions may begin to support more diverse communities earlier than others, acting as centers from which recovering faunas later spread. Elsewhere, harsh conditions delay recovery and maintain low-diversity microbial-dominated systems for extended periods. Throughout this earliest phase after the Great Dying, the oceans thus remain in a transitional state. They show the imprint of the catastrophic changes that mark the boundary, but they also contain the seeds of future diversification in the form of survivor lineages and slowly changing physical conditions. The prevalence of microbialites and other microbial structures on the seafloor captures this dual character. They are both a sign of ecological collapse, with complex reef systems absent, and a demonstration of the capacity of microbial life to organize environments and facilitate the deposition of new sedimentary frameworks under extreme conditions. As earliest Triassic time progresses, these frameworks, and the sparse communities associated with them, provide the starting point from which more complex marine ecosystems will over longer intervals rebuild within an ocean that gradually moves away from the most extreme environmental states of the late Permian crisis. On land in the earliest Triassic, the physical landscapes and ecological communities continue to reflect the deep disruption of the late Permian crisis, even as some signs of adjustment begin to appear. Across many regions of the former supercontinent, climates remain warm and in large areas arid or strongly seasonal. Continental interiors still experience high summer temperatures and irregular rainfall, with long dry intervals interrupted by intense storms. Coastal zones and some upland areas retain somewhat more moderate conditions, but the overall pattern is one of stressed environments. Vegetation, having lost many late Permian components, is dominated in many basins by a reduced set of stress-tolerant plants. Conifers and other gymnosperms that can withstand drought and poor soils occupy hill slopes, valley margins, and some coastal settings. Opportunistic spore-bearing plants colonize disturbed ground when moisture and temperature allow. Forests where they exist are often patchy and open, with canopies that do not fully close. Large tracts of land that once supported continuous woodland or swamp now present a mosaic of scrub, sparse trees, and bare or weakly vegetated surfaces. Soils are frequently thin with low organic content and signs of strong weathering under fluctuating moisture conditions. Red bed sediments, calcretes, and other features indicative of oxidizing semi-arid climates are common in many earliest Triassic terrestrial successions. Within this framework, terrestrial vertebrate faunas reorganize around a limited number of successful survivor groups. In southern Pangaean regions, assemblages dominated by small to medium-sized herbivorous synapsids such as Lystrosaurus are characteristic. These animals, with compact bodies, simple tusk-like teeth and limb structures, consistent with a combination of digging and walking, appear in large numbers in many early Triassic deposits. Their abundance suggests a generalist lifestyle and an ability to feed on a variety of plant material in landscapes where high-quality forage is scarce and patchy. By constructing burrows or utilizing existing shelters, they may avoid extremes of temperature and desiccation at the surface. Alongside them, other small synapsids, including certain cynodonts and therocephalians, continue as omnivores and predators, feeding on invertebrates, small vertebrates, and carrion. Early diapsid reptiles also occupy a range of roles from insectivores to small and medium-sized carnivores that hunt the abundant generalist herbivores and other prey. Large apex predators are relatively uncommon in many earliest Triassic assemblages, and where they exist, they are often smaller or fewer in number than their late Permian counterparts. This reflects the simplified state of food webs and the difficulty of sustaining high trophic level biomass when primary productivity is limited and vegetation remains degraded. Body size distributions in many faunas are skewed towards smaller animals. Rapid reproduction and shorter generation times permit these species to respond more quickly to short-term environmental fluctuations and to exploit transient windows of favourable conditions. Amphibians reduced during the crisis persist in regions where water bodies remain sufficiently stable, with some lineages occupying refuges along perennial rivers, in spring-fed pools, or in highland areas where local climates are more humid. Their diversity is lower than in the late Permian, but their continued presence indicates that not all freshwater habitats have collapsed, even if many are smaller, shallower, or more variable than before. Invertebrates on land, although difficult to sample comprehensively, in the fossil record show signs of limited recovery in some settings. Insect assemblages that survive into the earliest Triassic are less diverse than their late Permian precursors, but where vegetation stabilizes and soils regain some organic content, insect herbivores, predators, and detritivores reappear. Soil faunas rebuild slowly as plant cover returns in patches, contributing to the gradual improvement of soil structure and nutrient cycling. However, in many basins, evidence for extensive erosion course channel deposits and unstable floodplains indicates that the land surface remains prone to physical disturbance, and that soils are still in the early stages of reformation. Hydrological systems reflect the altered climatic and vegetational context. River channels in many earliest Triassic deposits are often braided or highly mobile, carrying variable loads of sediment from minimally vegetated catchments. Floodplains are broad and subject to frequent reworking, limiting the development of thick organic rich soils or extensive wetlands. Lakes, where present, may fluctuate greatly in level and salinity, influencing the composition and stability of aquatic and shoreline communities. These conditions reinforce the dominance of generalist and opportunistic species that can cope with rapidly changing habitats. Over the first several million years of the Triassic, there are indications that some regions begin to move away from the most extreme states seen at the boundary. As volcanic activity in the Siberian province declines, and weathering of uplifted and volcanic rocks continues, atmospheric greenhouse gas levels may gradually adjust. While climates remain warm, some reconstructions suggest that temperature and hydrological regimes slowly become less volatile in certain areas. In tandem, vegetation in these regions starts to diversify from its initial simplified state. New gymnosperm and pteridophyte assemblages appear, and plant cover becomes denser in a few basins. This allows more stable soils to develop with thicker horizons of organic matter and better structure. In such settings, terrestrial faunas can expand in diversity and complexity, with new herbivore and predator lineages appearing, and more intricate food webs forming. However, this recovery is uneven across the supercontinent. Some basins, particularly those that remain strongly arid or subject to continuing erosional instability, show delayed or minimal improvement in ecological complexity. In these areas, early Triassic faunas remain dominated by a small set of tolerant species for extended intervals. The contrast between basins that recover more quickly and those that remain stressed underscores the importance of local and regional factors such as topography, distance from the sea, and proximity to volcanic regions in modulating the pace and pathway of recovery. The overall duration of this early phase of post-crisis adjustment is long in human terms, extending over millions of years, even though it represents a relatively brief part of Earth's history. Throughout this time, the imprint of the Great Dying remains visible in the simplified structure of many ecosystems, in the absence of several formerly important clades, and in the persistence of physical and chemical conditions that differ markedly from those of the late Permian. The earliest Triassic land surface is in many respects a world in transition, not as acutely disrupted as during the peak of the Extinction, but still far from the more varied and structured ecosystems that will characterize later parts of the Mesozoic. Within this transitional world, the surviving lineages of plants and vertebrates continue to interact with the evolving climate, soils and hydrology, gradually building the foundations of new ecological combinations that will over extended time lead to the emergence of more complex terrestrial communities